So sorry, probably should have made this a bit more clear, but I had the transformation matrix and the original coordinates the wrong way round. It should be the transformation matrix times the original coordinates. I did do it that way round in the first video, which was about the reflections 90, 180, 270, etc. Well, etc. They're the only ones. Anyway, so it's transformation matrix times the original coordinates. Not what I was going on about, but the rest of that is perfectly correct. Okay, so sorry about that. Hopefully this won't happen again in another video. But what are you gonna do? I couldn't be bothered reading the whole video because it wasn't wrong. So anyway, so thanks for watching. Hopefully we'll see you in the next video. And I won't be adding another bit to this. I don't think. All right, see you soon. Hello and welcome. This is an FP1 video. This is going on with our idea of rotations, reflections, and enlargements of matrices. Okay. In this video, we're going to be looking at the reflections. Now, it's very similar to what we did in the last video, where we were looking at the rotations of matrices. We were rotating. We looked at the I and j unit-based vectors in terms of the I was essentially 1 in the x direction and the j was 1 in the y direction, okay? And obviously we looked at moving them, okay, by translating them 90 degrees, 180, 217, 360 degrees. Well, 360 would be obvious, it would just be where it is, so it doesn't matter. Okay, anyway, so as I said, what we did in the principle of that was we took the points of a shape, okay, the vertexes or whatever, and we multiplied it by something called the transformation matrix, which is made up by the end result of these movements of the I and j unit-based vectors. The first half was made up by the I unit-based vector, and the second half was made up by the j, the end result of the j unit-based vector moving. Okay, right. So in so in this video we're going to be looking at the effects of reflections in the x-axis, the y-axis, and y equals x and y equals negative x. I'm going to cram it all into one video. Okay, so alright, so say we've got, I'm thinking, see, what I was going to do, I was going to come up with that same shape I've used in the 2 previous videos, but why not? I'm not going to do that actually. Okay, so that might be a standard kind of shape, alright? And obviously if we're reflecting it in the x-axis, that's obviously the x-axis, then you put the mirror on the x-axis, so realistically it's going to look something like that, okay? Maybe, obviously, your art skills would be a hell of a lot better than mine. Okay, so anyway, what we did, as I said, we looked at the, essentially what we did was we took the shapes of the points, the vertex of the first shape, so the original points, I'm going to call it, the original coordinates, and we times it by the transformation matrix. And remember I said the transformation matrix, I'm going to label as TM, but because I'm lazy, okay, and then I've said that is obviously equal to the coordinates of the new shape, alright? But this transformation matrix, okay, so it's made up of the I and j unit-based vectors. Okay, so I'm going to draw 2 graphs here. So the first little graph is going to be the reflection of the I unit-based vector. Okay, so the I unit-based vector was 1 in the x direction, 0 in the y. In other words, 1, 0. But that essentially, as I said, that's the x-axis. So if you reflect it in the x-axis, nothing's going to happen to that shape. Nothing's going to happen to that base vector because it's on the line which it's been reflected in. So it's not going to have any effect here. Okay. Well, quite clearly, if you do that to the j unit-based vector, which has obviously coordinates 0, 1, when you reflect that, okay, it's going to give you, is that right? Yeah, 0, -1. Okay, so what we were saying is this transformation matrix is made up of the combination of the end result of the I and the j unit base vector. Okay, so we know the first half of this is the result of the shift of the I unit base vector, but because it doesn't move, we still write it in as 1, 0. But because the j component has sort of been reflected in the x-axis, it's 0, minus 1 as opposed to 0, 1. Okay, so that's your transformation matrix, and you would put in whatever coordinates you had for this shape. So if we call it top A, B and C, and obviously you were going to reflect it in the x-axis, which funnily enough is the exact same kind of shape that you would get by rotating it. Okay, but obviously you might have to do a bit of translation as well, but anyway, shut up. Okay, so that's a principle. And that would be the transformation matrix for reflecting in the x-axis. Okay, so that would be the shape for any shape that you would multiply. Obviously, the coordinates of each shape, weirdly enough, might be a little bit different, hintity hint hint, but the transformation matrix, that would be exactly the same. And it's not like the rotations where if it was clockwise or anti-clockwise, but quite clearly we're not talking about rotation, so you can't have an x-axis that's rotated anti-clockwise and reflected in the x-axis, because that's just a load of words, and it doesn't actually make sense. As just a, well, because the rest of what I'm saying hopefully does, although some people probably doesn't. Anyway, so that's a transformation matrix if you were reflecting in the x-axis. Okay, so 1, 0, 0, 1. Alright, so I'll just put that down here, because I'm obviously going to rub it off. 1, 0, 0, minus 1. And that's the transformation matrix for reflections in the x-axis. Okay, so hopefully that makes a fair amount of sense. Now, what we're going to look at is we're going to look at the reflections, but obviously now we've done the x-axis, we need to do reflections for the y-axis. Okay, so using the same principle as what we've just done, in terms of we're going to split up the I and j unit base vectors, okay, to enable us to get this other transformation matrix, which is obviously going to be for the y-axis. Okay, so we start with the same I and j unit base vectors. So let's see what happens to the I unit base vector. Well, it's reflected in the y-axis. The y-axis is essentially the mirror. Therefore, it's the same as rotating this 180 degrees anti-clockwise, which gets us the new unit I unit base vector of minus 1, 0. Okay, and obviously if we reflect the j unit base vector on the y-axis, well, it's already on the line it's been reflected in, so we don't change it. Now, just like as we've done for the previous one, the transformation matrix, the first half of this transformation matrix is made up from the end result of the I unit base vector, and the second half of it, the second column, I should say, is made up by the j unit base vector at the end one. Okay, so the end I unit base vector is minus 1, 0, and the end j unit base vector is 0, 1. Okay, so that's the transformation matrix is minus 1, 0, 0, minus 1. And that is for the transformation matrix whenever you are multiplying, when you're reflecting the shape in the in the y-axis. Okay, so I'm going to write that down. So that's minus 1, 0, 0, minus 1. Okay, and that's the transformation matrix for reflections in the y-axis. Okay, so now we've done the two sort of most common ones. The other two, okay. What we're going to do now is we're going to do reflections in y equals x and y equals negative x. Okay, right. So obviously, just to give you a little bit of a memory refresh,
As I said, you could do this by just sort of sketching some points if you totally forgot what the graph y equals x looks like. But I mean, every y coordinate is the same in terms of the x coordinate, so you get something that goes through the origin and looks like that. That's y equals x. But as I said, hopefully you should have remembered that. You didn't really need me to go through that, but just went through it anyway because I can. Okay, so hopefully, as I said, you would have already known that. It's a bit of a waste of time. Okay, so what I'm going to do is just put a dotted line in each of these unit-based vector graphs, okay? Because we're going to be reflecting it in the y equals x. Okay, so obviously the I component becomes the j component, and the j component becomes the I component. What I'm trying to say is when we reflect the I unit-based vector, it becomes the same coordinates as what the old j unit-based vector was, which is 0, 1. And then when we reflect the original j unit-based vector, well, it becomes the original I unit-based vector, okay, which is 1, 0, okay? So it is a little bit confusing. Anyway, the shorthand is the transformation matrix for reflections in y equals x is the end result of the end result of the I unit-based vector, which is 0, 1. And the second column is the end result of the j unit-based vector shifting or reflecting or whatever, which is 1, 0. Okay, so your transformation matrix for reflections in y equals x is 1, 0. Sorry, 0, 1, 1, 0. So transformation matrix for reflections in y equals x is 0, 1, 1, 0. Okay. Right, so what we're going to look at now is y equals negative x. Now for this, is as I said, what I'm going to do is actually just spend a short period of time. As I said, you probably are still in your first year if you're doing this, or he said it's very unlikely you might be in your second year doing this, but whatever. Okay, so what I'm going to do now is I'm just going to give a quick sort of refresh of your C1 knowledge of transformations of graphs. Yeah. Okay, sorry. So what I've done there is I've just wrote a few bits of sort of key sort of C1 knowledge, really, transformations and reflections of graphs. Okay, so basically when you do y equals, you do the negative of the whole function. Okay, it's a reflection in the x-axis. Okay, because you turn in all of the y coordinates, because if y is equal to a function and you turn that function negative, okay, you're reflecting it, but you're not reflecting it in the y-axis because the x coordinates are not going to change, it's the y coordinates that are going to change, so therefore it's a reflection in the x-axis. And when we do a function which is just negative for the x in that function, it's a reflection in the y-axis. Okay, so when we do y equals x and then we do y equals negative x, okay, we're doing a negative the whole function, not just the x, okay? So therefore, it's a reflection in the x-axis, okay? So therefore, what we'd normally have is this curve doing that, alright? But instead, what we've got it doing this, okay? Going through like that, okay? So hopefully, as I said, that makes some kind of sense. Right, so anyway, as I said, that was just really a quick recap of some C1 knowledge. Okay, so as I said, hopefully you should have been able to get that anyway. So what we're going to do is just do the same principle now. Right, okay, so when we reflect it in y equals negative x, okay, well we look at the I component first. Well, it's not going to reflect, it's not going to move to the original point of the j component, it's going to move over here, okay? So reflected in this line, 1, 0 is obviously going to become 0, minus 1. And when the 0, 1 line is reflected in y equals negative x, well, it's going to become minus 1, 0. Okay? So the transformation matrix is made up of the first column is the end result of the I unit-based vector, whatever that ends up being. Okay, after that's rotated, reflected, whatever. And the second column of the transformation matrix is made up what happens to the j unit base vector. Okay? Okay, so therefore the transformation matrix is 0, minus 1, minus 1, 0. And that's the transformation matrix for reflections in the line y equals x. Sorry, y equals negative x. Okay, so therefore transformation matrices, you don't need to know them. Well, it'd be helpful. I'm not entirely sure. I really doubt very much they're in your formula sheet. But they might be. Have a look. As I said, I probably should have checked it out before I did this video. But what you can do. Anyway, so as I said, really you can just come up with them yourself. You know, in the exam, do a little note at the side. And so it only take you a few seconds. It'd probably take you longer to look. Try and find it in the formula sheet, to be honest. But you know, depends what kind of if you can read or not. Anyway, so as I said, the principle of what we've done so far, so you know, looking at rotations and reflections, is always the original coordinates times the transformation matrix. And this transformation matrix, the first column is made up of the end result of the I unit base vectors, and the second column is made up by the end result of the j unit base vector. So just move out of the way so you can kind of take all that in. Okay, so I put a little note, obviously, next to each transformation matrix, what it is for. Okay. As I said, I've not come up with the coordinates for this and applied it like I did in the other video, purely because, well, you know how to multiply out matrices together. And as I said, there's a whole video on that, so I can't be bothered, to be honest. It's a shorthand. Okay, so thanks for watching. Hopefully it's been of some use to you, and we'll see you in the next video, which will be enlargements.